Moving on with exponential functions and compound interest. So we've learned about compound interest and we've learned about E, but there's actually a time where we need to combine those two things together, the number E with compound interest. And so that's what we're going to be learning about here. So first I'm going to present you an example. We have the formula as defined before, amount equals principal times 1 plus our rate over the number of times compounded, all to the n times t, where t represents time. So we have $5,000 that's invested at 6.5% interest, and we want to determine the total amount after 10 years, depending on how we compound it. So we want to compound it annually, once a year, quarterly, 4 times a year, monthly, 12 times a year, daily, 365 times a year, and then what does it mean to actually compound it continuously? So I want you to do parts 1 through D on your own after pausing the video, and then we will come back and we will discuss part E, how to compound this continuously. All right, so at this time you should have worked through parts A through D, and here's the formula that you should have had. So the variable that's unknown or that varies in this one is the number of times it's compounded, and so that's why we have n as unknown, and that's why we substitute it in for all of these places. If it's compounded annually or one time, we get this $9,385.69. If it's compounded quarterly or 4 times a year, we get $9,587.79. 12 times a year, we get this amount, and 365 times a year, we get this amount. And so you can see how the number of times it gets compounded a year can greatly affect how much money you have in your account at the end of that time period. But what does it mean to actually compound it continuously? Well, if we wanted to figure out how many hours there were in a year, we could definitely do that, and we could substitute that in. Maybe we wanted to figure out how many minutes there were in a year and try that, or how many seconds there are in a year and try that. And that might be getting close, but if we want to compound it continuously, that's even more defined than every second. And so we're going to need to alter our equation a little bit. So what I'm going to do is I'm going to start with the same equation that I have here. I'm going to make a couple little tweaks to it. So the first tweak is notice that instead of using n, I'm using k. But no big deal. K still stands for the number of times it's compounded per year. So all I'm doing is switching out variables, and that's no big deal. I'm only really doing this to switch with the consistency of the textbooks. One of the textbooks I was referencing earlier used the variable n. This textbook that I'm referencing now is using the variable k. So the number of times it's compounded per year. And then if we want to figure out how we can adjust this to be continuous, we're going to alter our formula even a little bit more. So what I'm going to do now is I'm going to let a variable, I just randomly chose n, but I can pick any variable here, and I'm going to let this variable be k over r, and I'm doing it very strategically, and we're going to do that to alter this formula here. Okay, so we're going to have to make a couple of tweaks. Notice in our original formula, we have r over k. So we want to figure out how can I change that to put it in terms of n. So let me start with r over k. I know I'm going to want to change that to be k over r because that's how I'm defining n. And so I know I can tweak that by basically taking it to a negative exponent. And so that means it's the same thing as taking n to a negative exponent. Or it's the same thing as taking the reciprocal of n. So I'm taking what was originally in the formula, and now I'm going to replace it with this 1 over n. And all I did was alter it using this information here. So my formula now becomes 1 plus, instead of r over k, now it's going to be represented by 1 over n. Now also, I want to take out this k and I want to put it in some version of n. So let me take this exact formula here, n equals k over r, and I'm going to solve it for k so I can substitute it in for this k. Well, if I want to solve for k, all I need to do is multiply by r on both sides because it would cancel out here. And so that tells me that k is equal to n times r. So that's what I'm going to substitute in for that k value there. N times r. And then, of course, you can't really see it, but then, of course, I still have this t in my equation. Okay, now I actually have this formula exactly where I want it to be. If I were to look at this portion of the formula, we've actually seen that formula before. We saw it when we were trying to come up with the number e. We saw it right here, 1 plus 1 over n to the n value. That's exactly what we saw. And notice as n increased, this value, this whole value here, got closer and closer to our letter E. What does that actually mean? That means if we look at the limit as n increases indefinitely, n approaches infinity, of this 1 plus 1 over n to the n power, that is going to be our exact value of E. So, if I go back to this, and if I want to see as n increases indefinitely, hence compounding it continuously throughout the whole year, every single instant that we can possibly think about it, this is going to be represented by E. And so now we have the formula of A equals P times E to the RT. And so this is exactly the formula that we will be using if we want to compound it continuously. So, if I were to go back to my exact example, and if I wanted to compute part E, I would actually using my new formula, A equals P times E to the RT. And so I can use that in figuring it out here. So my principal is $5,000. E stays just the way it is. It's the number in itself. My rate was 0.065, and my time was 10 years. And so all I need to do now is type this in my calculator to figure out what my actual amount after 10 years is. So pulling up my calculator here, I have 5,000 times E to the 0.065 times 10. And we see that our amount compounded continuously throughout 10 years is $9,577.70. So our answer here is $9,577.70. And so that is our answer to compounding continuously. Okay, so let's recap what we know so far. Right now we have our compound interest formula, A of t equals this. If we know the actual number of amount of times, we're going to compound it per year. Or it's going to be represented this here if it's going to be compounded continuously. All right, now notice I said I'm going to switch the variables because of the textbook issue before. I'm going to do that exact same thing here. So typically we've been using A for amount. Instead of amount, I could also be talking about a balance. So let me just tweak these variables one more time. Instead of A, I'm going to be using B. The balance at the amount of a certain time frame is going to be this here. So exact same formula, I'm again just switching variables. And it's going to be the exact same thing if I were to compound it continuously as well. So instead of letting A represent amount, we're going to let B represent our balance. Now, I didn't specify this before, but this is, of course, a balance of a future value. If we invest a principal amount now, what do we get in the future? What's our ending result? So, some instruction wording that you might see is compute the future value. So normally we would just say compute the value because we would probably think what's happening in the future. but it has to be specified because of our next example. So I'm going to tweak it one more time. Instead of the future value, we might want to know if we wanted a targeted value in the future, how much would we need to invest today? And so that's what's going to be called computing the present value. So an example of this might be if you want $1 million for retirement in however many years, how much do you need to invest right now? And so basically what we do is we take the formulas that we saw before, our compound interest formulas for the future, and we tweak them and we invert them. So notice our formulas are almost identical except for, notice our principal and our balance are tweaked. And notice our exponent is now negative. So basically we've taken the inverse of the function because that's what we're doing. We want the inverse of our future value is the actual present value. So these are the formulas that you'll be using, and now all we have to do is plug in numbers to figure out what our present value is. So I have an example here. Faye is about to enter college. She knows at the end of her 4 years she wants to take a trip to Europe, and she's estimating that it's going to cost her $5,000. So how much does she need to invest right now at 7% to have enough for the trip if interest is compounded A, quarterly, or B, continuously? So you have the formulas right here in front of you. I suggest that you pause the video and figure out what the present value is for this example. Okay, in part A, we have this formula because we know it's going to be compounded 4 times a year. And so we have our present value at the end of 4 years is our ending balance of $5,000 times 1 plus my rate of 0.07 over 4 times it's compounded to the now a negative exponent because I'm doing the inverse. The number of times it's compounded is 4 and the amount of years is 4. And so all I need to do is type this in my calculator. So I have 5,000 times 1 plus 0.07 divided by 4 to the, and I can do all that math in my head, negative 4 times 4 gives me negative 16, so I'm just going to type that in. And we can see that if she wants to make a one-time investment right now with all of those stipulations, she would need to invest $3,788.08. And so our answer is $3,788.08. The second question is, what if it's compounded continuously rather than quarterly? Well, continuously means we're going to use this formula. So at the beginning of her 4-year period, she wants to still end up with $5,000, and then e to the negative, my rate was 0.07, and my time is 4 years. So all I need to do is type this into the calculator, 5,000 e to the negative 0.07 times 4. And so this amount is $3,778.92. So $3,778.92. And so there are the 2 answers for the present value, knowing what she wants in the future 4 years from now. All right, I have one more example of compound interest, and so you'll see that in the next video.